Today's video, here is a nice problem that was suggested by viewer. Here is the following statement: determine all prime p such that we have this following setup. We have number 1 plus p square plus p cubed is a perfect square. Okay, so we are going to find a p as a prime number where we can have the whole term as a perfect square. Okay, in fact, this is very nice and interesting problem to work on. You guys, you can give it a try to problem pre get into the solution. Go ahead, pause this video anywhere you come back to see the full solution. Okay, now let's jump into the solution now. So we have this following setup. This is a perfect square form, is noted as x square. Okay, so we are going to skip unnecessary things here. So for the even prime, we shouldn't prove that because it's very clear. This one, it's clearly is an odd prime, because as you plug in number 2 here as an even prime, is not giving you a perfect square. Okay, it's giving you 8 4 plus 2 plus number 1. The total is giving us 15. 15 is not perfect square, which means is an odd prime. Okay, so let's jump into this one quickly. Since we have x square here, we have number 1 here, it's a good opportunity where we can have a difference of two squares after moving over number 1 to the right. Okay, so I will have the following expression. You get p, and also I'm going to take this p as a common factor. You will get p is multiplied by 1 plus p plus p squared equals x minus 1 factor x plus number 1. Okay, I'm doing this one right away. It's very clear here. After you take number 1 to the right, you get a difference of two squares. Then we factor out that, we get to this expression. Okay, this is very nice expression. Now we'll have two things here. Since the left hand side, since p is dividing the left hand side of this equation, because p is involving this product, which means p must be divided the right hand side of this equation. But the problem with, we don't know which term p divides. Okay, so we may have p divides x minus 1 or x plus number 1. So we must go through two cases, or we are going to force one of those must be out of this possibility in order to continue on that one right here. So by the way of contradiction, suppose p divides x minus number 1. If p divides x minus number 1, which means p not divides x plus number 1 based on our assumption. Okay, because if you take a look carefully at both terms, we have GCD of x minus number 1 and x plus number 1 equals 1. Why GCD of these terms equals 1? Because they are odd consecutive terms. Why x minus number 1 and x plus number 1 are odd numbers? Because x is even. Why x is even? Because the left hand side of this equation is even. So since we have two informations here, so I'm going to take advantage of both facts. So this one, I'm simply going to apply the Fermat-Leroy theorem, because we have p as a prime not divides this integer, which means starting with this one. So we know p not divides x plus number 1. This implies x plus number 1 to the p minus number 1 is congruent to 1 mod p by Fermat-Leroy theorem. Okay, then by using the second rule here, so I have p divides x minus number 1 according to the divisibility statement. I get x minus number 1 equals m is multiplied by p. What is a m? Is some natural number. Okay, or positive integer. Because we have x is a positive integer, since the left hand side of this equation is a positive, because we are working on the prime numbers, so everything is positive here. Okay, we don't have to worry about the negative numbers here at all. Okay, so taking this number minus number 1 to the right, I get here x equals mp plus number 1. Okay, taking this value of x and plug it back in previous expression, which is this one. Okay, so I get here m and p plus number 1 plus this number 1 plus the whole thing is raised to the p minus number 1 is congruent to 1 mod p. Here is a thing here. Here is a thing here. So we know the exponent is even, because p is odd minus number 1, it becomes even. So if we want to take the exponent off, we must take two possibilities, plus or minus 1. But the problem, when we pick up the positive number, we pick up the negative numbers. We're talking about the negative numbers when we have this one is negative, okay? But this one is positive. We know m is a positive integer, p is a prime, plus number 2, so everything is positive. So we don't have to worry about the negative option, okay? So we are going to take the positive one. So by taking the exponent of, I get m p plus number 2 is a congruent to 1 mod p, okay? Cancelling number 1 on both sides, I get here mp plus number 1 is a congruent to 0 mod p. What's this one telling us? It's telling us p divides this term, okay? This one is telling us p divides mp plus number 1. If p divides mp plus number 1, so according to the divisibility notion here, so we'll have mp plus number 1 equals k is multiplied by p. What is a k? Is a some natural number, okay? Then I'm going to leave number 1 as it is, just moving over mp to the right, okay? I get number 1 here equals k pi minus mp, then taking p as a common factor for both terms, I get p is multiplied by k minus m. So we have this fact, we have ended with this fact. Number 1 equals to this product. This one is telling us number 1 equals p and number 1 equals k minus number 1, k minus m. It's clearly a contradiction because p is an odd prime. P cannot be equal to 1, okay? Where we have contradicted our assumption. The assumption that we have chosen, it was not true, okay? What does mean? That means p not divide x minus number 1, but p divides x plus number 1. So one is telling us p divides x plus number 1. I'm going to put this one in the purple box here. So, and the Karen are going to work on these facts, okay? At the same time, p not divide x minus number 1 because of the GCD equals 1. Both terms equals 1, which means if p divides this one, which means p cannot divide x minus number 1. Now we are ready for the next step, which previously we were arguing to prove p divides x plus number 1 and came up with this nice result, which is true. So we know p divides x plus number 1, so I'm going to use this fact in order to find p, okay? So what this one is telling us, p divides x plus number 1 according to the divisibility statement, x plus number 1 equals k is multiplied by p. What is a k? Is a sum natural numbers, okay? Then using this fact and taking this x, so we'll have x equals k pi minus number 1, taking this value of x and insert it back into the previous equation, which is this one here. So I will have the following. I will have 1 plus p squared plus p cubed equals k p minus number 1 quantity square. Foiling this one, expand this one out, I get k squared p squared minus 2 times k p plus number 1. So the nice thing here, when we have number 1, is going to cancel out from the left and the right. Also, we will have one of the p will be cancelled also from the left and the right, because dividing both sides by p, the p is going to cancel out. We don't have to worry about when we divide both sides by p, because p is an odd prime, so it's different than 0. So which means I will have a reduced expression, which is 1 plus p squared equals k squared p minus 2k, because I have divided both sides by p. That's why I have this simple expression. Okay, then what's the next thing coming up? So I'm going to fix one variable and leave the other one as a constant. So which one be a constant, which one a variable, which one be a variable? Let's consider p as a variable and q as a constant. So we have p squared here, then taking these both terms to the left and also make p as a common factor here. So I have 1 minus q squared is multiplied by p plus this number 1 plus 2k equals 0. Okay, now we are going to calculate the discriminant of this one, which is delta. So we get delta equals 1 minus q squared quantity square minus 4 times 1 plus 2k. By simplifying this one out, I get number 1 here minus 2 times q squared plus q to the 4th, okay, minus number 4 minus 8k. Okay, then simplify this expression. I get here q to the 4th minus 2 times q squared minus 8k minus 3 plus number 1, which is minus 3 here. Okay, so this is delta. So in order to have a solution for this equation, so we must have delta as a perfect square. Okay, so we need to check the status of this one and figure out which condition can make us a perfect square here. Okay, so I'm going to take this delta as we see it there. Delta equals q to the 4th minus number 3, definitely strictly inferior than q squared minus number 1. Okay, if I'm going to distribute this one, the first term is given as q to the 4th, which is good to go. The middle term is given as minus 2q squared, which is good to go also, plus number 1. So this term is still always smaller than this term, whatever the term of k is. Okay, have inequality is verified here, all k. So even if you have k equals 1 as a minimum value, you still have this inequality holds. Okay, but the problem, we are going to check the other side, so the left side of this inequality. So the other side, I'm going to create the number which is less than this one. Let's put it k squared minus number 2 quantity square. Now we are going to check the left hand side of this inequality, which condition we can give to the k to make this inequality holds. So that I'm simply going to expand this one and make the comparison between this delta and the left hand side of this inequality. Okay, so this one is given as simply q to the 4th. By expanding this one out, I get minus 4 times q squared plus number 4 is strictly inferior in this term, which is q to the 4 minus 2k squared minus 8k minus number 3. Some stuff will be cancelled out from here, q to the 4th, and then take everything to the right. Minus this 4 minus 3, which is minus 7. So I'm going to flip this inequality. I get here 2k squared minus 8k minus number 7, strictly superior than 0. Now we are going to check which the condition of k can make this the whole thing strictly superior than 0. Okay, by guessing, check number by number. This one holds if we have k is superior or equal to 5. Okay, because this fact is providing us with a nice information to tell us this delta, which is this one, is between two consecutive squares, which is q squared minus number 1 quantity square and q squared minus 2 quantity square and q squared minus number 1 quantity square. But which condition? The condition when we have k superior or equal to 5. But since delta is situated between two consecutive squares for all k superior or equal to 5, which is impossible. Okay, because delta is a perfect, which is impossible, which means k not superior or equal to 5. K must be strictly inferior than 5. In the other word, key is taking this set, number 1, number 2, number 3, and number 4, not number 5, not include number 5. Okay, previously we're working on this one just to determine key. Now we found this key taking these 4 possibilities, but we don't know yet which key is appropriate value can make us a solution for this equation. Okay, so we are going to use this equation and these facts in order to find x. Okay, so let's take case by case. Case number 1, k equals 1. I will have x equals, by plugging k with number 1 here, I will get p minus number 1. Taking this fact and plug it into the origin equation, so square. Expand this one out, I get p square here minus 2p plus number 1. Cancelling out number 1 from the left and the right, cancelling p square from the left and the right, cancelling p from the left and the right, p square equals number 2 here. Okay, this one is telling us p square equals 1. It's clearly a contradiction. It's impossible because p is an odd prime. Okay, now let's move on to the case number 2. Doing the same thing, I will have x equals 2p minus number 1. Plug in all this information as I did in previous equation, like this. Distribute this one out, I get 4p. Doing the same thing, I'm going to prove this one by using a small trick here. So I get p minus 2 quinary square. Distributing this one out, I get p square minus 4p, but I have minus 3p here. I get plus p here. Plus number 4, I already have number 5 here. So which means I adjust number 1 here, equals 0. Taking these 2 facts to the right, I get p minus 2 quinary square equals minus p plus number 1. We know this is positive number, but this one is negative, which it's clearly a contradiction. So let's move on to the next case. Case number 3. K equals 3. K equals 3, by doing the same thing, I will get x equals 3p minus number 1. Taking this fact, plug in the previous equation, I get 1. Taking p as a common multiplier, I get p squared. Since p is an odd prime, which means this one equals 0. Okay, delta, I will get h squared is 64 minus 4 times this one, I get 64 minus 28. 64 minus 28 is given as 36, which is 6 squared. Then I will have the following solutions. I get minus 8, which is 8, plus square root of delta, which is 6 over 2. The second solution, I get the same thing, 8 minus 6 over 2. This one, 8 plus 6, 14 over 2, which is 7. Now we found the prime p equals 7, but this one is not a solution because p2 equals 1. Okay, so we are going to keep this solution. Now we found one solution here, which is p equals 7. Let's check the last case. 1 plus p squared plus p cubed. By plugging number k with number 4, I get 4p minus number 1 quinary square. Okay, so I get here 16p squared minus 8p plus number 1. Number 1 will be cancelled out, so I'm going to use a trick here. I'm going to take 8 as a common factor here. Becomes 2p squared minus number 1. Okay, the left hand side of this equation, this is odd. Putting 2 primes together is giving us even, plus another p is giving us odd. But the right hand side of this equation is an even. It's clearly a contradiction, which means we have no solutions. The only solution that we found was p equals 7. Okay, if you have ended this video, if you have any question or suggestions, put it in the comment section below. By the way, don't forget to support us with your like and subscribe. Thank you for watching. We'll see you next video. Bye.